Okay, so let's get down to the actual business of solving the equations of motion that we found in the last video. So just as a reminder, we are solving the problem of linear drag, where we have air resistance on a projectile particle. And we'll start now by working in the horizontal direction. And in the horizontal direction, the equation of motion we found was this one. So this is now written in terms of position, and there it is a second order differential equation. But by working with velocities first, we can transform it into a first order differential equation. So then we just have mv dot equals minus bv, or v dot equals minus b over m v. So we could solve this by direct integration. That's not hard, but this is such a common differential equation that you should be able to just recognize the solution. There's only one function that is proportional to its own derivative, and that is the exponential function. So the solution we have here is just the following. We get v of t equals some constant a times e to the minus b over m times t. And that's the solution. I'm going to rewrite it slightly differently here, though. I'm going to write it as v of t equals v0x, because a here is the initial velocity of the projectile, times e to the minus t over tau, where tau equals m over b. Like so. If you plot this, it will look like this. Let me make this slightly smaller so that there's room for it here. So this is the velocity in the x direction as a function of time. The initial velocity here is v0x, and tau in time is somewhere around there. Tau is what we call the decay time. It's the characteristic time for the projectile slowing down in the x direction, and it's equal to m over b. It is the time that it takes for the projectile to slow down to a factor of 1 over e of its normal value, of its initial value, which is about 37%. So if we look at this, that becomes about 0.37 v0x right there. So that's the velocity. Now, in order to calculate the position as a function of time, we note that when we went from here to there, we actually left out one fact. Let's use black. And that is that v is x dot. In other words, dx dt. And that can be our second differential equation. So we have here that the x to t equals v, or that the x equals v dt. And then we integrate this. X goes from 0 to x. Right? Remember, we're starting out at the origin, where x equals 0. And same thing in time. We start out at time t equals 0 and go to the present time. And we're changing the names of the variables here in the integration to make things simpler. On the left-hand side here, we have only x minus 0, right? Equals the integral now of, from 0 to t, of v0x e to the minus t over tau. And that's, of course, v0x, etc. And this t prime there. And that's the result in the x direction of the x position. We can plot this as well. It looks like this. So this is the x versus t. We can see here that when the time goes to infinity, x reaches a maximum value. That's this value here. This is x infinity. Let me make it a little clearer. X infinity, which is the maximum value that the x position can take. Like that. So what we have here is x infinity. Okay, that's the farthest we can get. No matter how long we wait, we're not going to get further than that from the origin. So x infinity is v0x times tau, which is v0x times m over b. So that means that a heavier projectile will go farther. A faster projectile will go farther, and the less drag you have, that is, the smaller the b is, then the farther you can go. So that's the horizontal direction. And now we'll do the same thing in the vertical direction. And in the vertical direction, we have the following equation. Which we can rewrite as, which I will rewrite as this. For reasons that will be obvious soon. To make this a little simpler to solve, we will choose a change of variables. I'm going to pick u equals v sub y plus v tur. And then we end up with, and that again has a very simple solution. That's the exponential equation once again. So we have, and then we'll put back in the change of variables. Now, at t equals 0, we have that the velocity in the y direction is v y0. So therefore, and that gives us the final solution here. Like that. And if we plot that, it looks like this. Okay, it's very similar to what we saw earlier for the motion in the x direction, but now we're dealing with a velocity. What we're seeing here is that it's actually starting out at t equals 0. This term goes to 0, and we're starting out at only vy0. So this velocity here is vy0, and then after some time we are asymptotically approaching this velocity up here. And if we look at the formula, we can see that at large times these exponentials go away, and we're left only with v tur here, and tur stands for terminal. So v tur is the terminal velocity. Essentially what is happening, and is that we're starting out with some velocity, which might be 0 or not. But as time goes by, we will approach some terminal velocity where the force of gravity is exactly balanced by the drag force that's acting on the projectile. And that's v terminal. like we said, V terminal is given by this. So the larger mass and smaller drag means larger terminal velocity. Okay, so now we have the velocity, but we still want to find the position as a function of time, and we're doing the same thing that we did in the horizontal direction. We know that dy equals v dt, and we can integrate from the origin to y, the beginning of time to t, like that. That gives us that y, which is this integral, equals then the integral of v sub y of t prime dt. That's the integral of this. I'm not going to show you the details. You can do it yourself, really. This becomes equal to the following. Like that. So that's the solution to the motion in the y direction. Okay. We have now both x as a function of time, and we have y as a function of time. So let's see if we can find y as a function of x using this. Actually, I see I copied the wrong thing here. Hold on a second. Now, solving this is relatively simple, but since we can do it quickly here in a recording, I'll just show you the algebra in case you are interested. Now let's compare this to what we get in vacuum. So just recalling from a little bit earlier, in vacuum, okay, which is the well-known parabolic formula. And if you plot this, well, these two trajectories, it looks something like this. And the exact relationship depends on the values of tau and v terminal, but essentially this is what it looks like. So the black curve here is the trajectory in vacuum, and the red curve is the trajectory under linear drag. And we can see here that initially both trajectories behave very similarly, but as time goes by and the drag has time to work, it turns out that the drag, in the presence of air resistance, the projectile ends up significantly shorter away from the origin than when you started. Of course, if the drag is weak, then this range will become closer to the vacuum range. There is the value that we found before for x infinity is somewhere around here, and that's the that is what this curve asymptotically approaches if we are shooting this projectile off a deep cliff. Here, this is the range in vacuum, and this here is the range in the presence of the linear drag. What we're going to do next now is calculate what this range might be. We hit here under the circumstances that y equals 0 and x equals the range. So our goal is to find r, and that corresponds to setting x equals r and y equals 0, just like it was before in the case of the vacuum trajectory. And if we do that in this formula here, we will just find so this is unfortunately a transcendental function, or a transcendental equation. And that means it can't be solved explicitly. We can do it numerically, but we can't explicitly solve this for the range R. And I don't know about you, but it's a little hard for me at least to look at this equation and get some insight into what the range actually is as you vary some of these parameters here. Now, we can do this kind of plots for a range of different parameters, but it's always better to come up with a mathematical expression that captures all the physics that we're interested in. So in order to do that, we're going to do a development of this logarithm here in terms of its Taylor expansion, and that will make things simpler. That's something that is valid and that is okay to do if this value is small. That corresponds then to low air resistance. So let's say that we have which means that r over vx0 times tau is much less than 1. Under those circumstances, we can use that ln of 1 minus x is approximately equal to the following. And we can then use that on this equation, and this becomes a little bit of algebra, but we'll go through it quickly. And then the logarithm will be replaced by this. So we'll rewrite this. Then we can do some simplification here. Looking carefully now, we can see that this term here is the same as this term there. So this cancels that. This equation was, of course, equal to 0. And we can see we can make one more simplification. We can get rid of a factor of r. Then we'll move this over to the right-hand side and multiply the equation by -1. And then we will get then we'll put in the expressions for tau. Remember that tau is equal to m over b. And I forgot a tau here. There. And we see immediately here from this that for low air resistance, actually for zero air resistance, B goes to 0, and then we recover the vacuum value of the range. Just remember that R vac from earlier is just T 2Vx0 times Vy0 divided by G. That's the first term here. And then we get some reduction, which becomes larger the larger the air resistance is. Now, for low air resistance, we can say that R is approximately equal to R vacuum. So that means that we could replace this with R vacuum, and we get that R is approximately equal to R vacuum This is, by the way, akin to perturbation theory, which you will encounter later in other courses. So with this, we can rewrite if we make the substitution here that V terminal equals tau times G. Okay. And then we can, after the fact, justify this approximation we made here by just noting that V0y might be much smaller than V terminal. So this approximation is valued if V0y is over V terminal is much less than 1. In that case, this is already true. So this is a technique that you can use rather often when you're dealing with a solution that you can't get an exact expression for, but is close to an exact expression that you already have. In this case, we were dealing with the motion of a projectile, which under vacuum conditions we know exactly what the solution is for, but in the presence of drag we couldn't write it down. So then we made this type of expansion in terms of a Taylor expansion, kept just the first few coefficients, the first 3 in this case, and we came up with this expression here for the range of the projectile, that although it's not exact, it is a rather good approximation in the limit of low air resistance. And this is something that you can use in many other contexts as well.